Okay, good morning, everyone. Could somebody ping the chat room to make sure that's working? Welcome back to Organic Chemistry 2341, Organic Chemistry 1 here at Texas State. And we are going to continue on with the Sn2 reaction. Remember, we're talking about S meaning substitution, N meaning nucleophilic, and 2 meaning bimolecular, meaning the nucleophile and the substrate have to be there at the exact same time. So let me go ahead and share my screen. And we'll continue on with some of the parameters that affect let me move the gallery up here. There we go. That affect this reaction. It controls the rate and or product ratios that we have in our system, okay? So having a lot of nucleophilicity controls the rate of the reaction, the kinetic measurement. However, the nucleophilicity is affected by charge. We talked about that already, how if it has a negative charge and or a polarizable charge, it can be a better nucleophile. Basicity, how strong a base is it? We calculated the pKa for its conjugate acid and then subtracted it from 14 to give us our basicity. Remember, we're always moving from the strongest base to the weakest base. Then we talked about polarizability, how the molecules that can easily pull electrons away to start forming that bond react faster than those that can't. So iodine, the big fluffy iodine, can react faster than fluorine. Okay, but now we have to talk about solvent. Okay, because solvent can actually change that polarizability. And then we're going to look at substituent effects, like how does if it's big and bulky or where the substituents are can affect the rate of the reaction based on that. So let's move up to our solvent right here. And in the solvent effects we have to think about what kind of solvent we're using, okay? If we're using number one, they all have to be a polar solvent because a polar solvent has to support the ion. Okay, for example, the fluoride ion or whatever the nucleophile is needs to be supported by the solvent. So we almost always use polar solvents to help support that nucleophile in its charged state or support that nucleophile in its neutral state as well. So in the case of water, water is what we call a polar protic solvent, meaning it can hydrogen bond. Okay, any solvent that can hydrogen bond, water, alcohol, carboxylic acids, are what we call protic solvents. Okay, and those protic solvents hydrogen bond to the negatively charged nucleophiles, making them surrounded by the solvent cage. So we have this surrounding of the solvent that can come in. Now, we now have to think about the type of hydrogen bonding we have. For small ions, we have a very tight shell of hydrogen bonding around it to support that ion. Because remember, it can't support that negative charge is in a really small place. You can't really support it very well. And so it has a strong hydrogen bonding shell of solvent around it. So if you think about it, that ion is not the ion by itself, it's the ion with the whole solvent around it that's trying to come in and act as the nucleophile. Okay. In the case of iodine, iodine is a stronger conjugate acid, and therefore it is bound less tightly by that hydrogen bonding shell, and it can be stretched by its polarizability to come in and give it start forming that bond more easily. So when we're talking about a polar protic solvent, if it's a smaller ion, it's more tightly hydrogen bound. Bigger ions are less tightly hydrogen bound. Okay, so that affects its reactivity. That makes that in protic solvent, iodine is more nucleophilic than fluorine. Okay, so the next thing we have to talk about is that whole concept of what's actually being supported here. Well, number one, the nucleophile has to be supported by that protic solvent, and it has this tight shell around it. However, the leaving group is the next thing that's going to be hydrogen bonded to. So the ability of the water to surround that leaving group and get it ready to leave is also important for our system. Okay, so in this polar protic solvent, because of this tight shell and loose shell, Our iodine is more reactive than bromine, bromine is more reactive than chlorine, and fluorine is the least reactive of the set. However, if we change the type of solvent to be a polar aprotic solvent, so it's a polar solvent that does not hydrogen bond, we get a different type of interaction. In the interaction we get with that solvent effect, we get what we call that dipole ion interaction. Remember, the dipole ion interaction is much less strong, much weaker than the hydrogen bonding. And so we see a different effect here. In the case of here, with the polar protics, we can do it where the ion is being hydrogen bound. This is a much tighter bond, and it can stabilize that ion very well. However, in the case of our aprotic system, we only have that dipole. So Rebecca, do you have a question? Your mic's on. So, all right. Okay. There, okay, thank you.
Sorry.
Okay, no problem. So in this case, it's less tightly bound, okay? And when it's less tightly bound, it's not as easily stabilized. So that solvation effect does carry the number of molecules that can be around it stabilizing that charge. Now notice in this, it only has a couple things that are stabilizing the charge. And in this case, that can make it more nucleophilic because it is less tightly bound around the system, around the anion coming in as our nucleophile. Okay. So the problem is that in halogens, it's actually reversed when we go from a polar protic solvent to a polar aprotic solvent. In the polar protic solvent, we're looking at that hydrogen bonding around the small ion is stronger than the hydrogen bonding around the larger ion, the iodine. However, if we go to a polar protic solvent, we now only have that dipole interaction. And so that dipole interaction is not as strong. And it turns out that it reverses the trend. In polar protic solvents, iodine is more nucleophilic because it's less tightly bound, okay? But in the case of polar aprotic solvents, chlorine is more reactive because fluorine is more reactive because fluorine is less tightly bound, and therefore it makes it much more of a negative charge that is more likely to react. It's less supported by the solvent, so it's actually more nucleophilic, okay? So in the case of these polar aprotic solvents, fluorine is more reactive than chlorine, chlorine is more reactive than bromine, bromine is more reactive than iodine. So when you're looking at something and you're saying, hey, you know, I have this ion in my system, I need to look at the solvent to see where the equilibrium of this reaction will lie. So if you did the reaction in water, you're going to end up using iodine as the nucleophile. If you do the reaction in acetone, you might end up with fluorine as the one being the nucleophile. Okay. So in an Sn2 reaction, we're looking at a biomolecular reaction. It's exothermic reaction. The products are always less energetic than the starting materials, okay? In the transition state, there's a single transition state and a single hump in our reaction diagram, okay? The rate is dependent upon the concentration of both reactants, both the nucleophile and the electrophile. It's also the nature of the leaving group. Whichever ion is the weaker base is the one that where the direction of the equilibrium will lie. So you look at your pKa's and you find out, and then you take 14 minus the pKa, whichever one is the higher number, the pKb, that's the weaker base, and that's the direction your equilibrium will lie. Okay. When we have strong unhindered bases, for example, alkoxide or OH, these are good nucleophiles because they have a charge and they're small and they're not hindered by sterics. Okay. So whenever we think about these reaction mechanisms, you need to look at the electronics, you know, the energy of the system, which is, are we going to be exotherm or endotherm, and the sterics of the system. Almost every reaction is controlled by those energy and the sterics. Okay. So now if we have a big hindered base, or the classical is T-butoxide, anything with a large group next to it, now this becomes a poor nucleophile because of sterics. We still have an anion on oxygen, just like we had here, but it has to have much more energy to come in to form that because it has much more electron repulsion because it's so big. Okay. The next thing we saw, it was polarizable bases are good nucleophiles. So things like that are big and fluffy, like iodine and bromine, are good nucleophiles. Less polarizable bases are poor nucleophiles. Now notice also these uncharged systems with lone pairs are also poor nucleophiles. And then the next thing that happened was solvent. All polar aprotic solvents don't bind as tightly to the ions, and it can change the reactivity. In fact, it completely reverses the reactivity in the case of the halogens. In polar protic solvents, and actually that's what a lot of our Sn2 reactions are run in, it helps the reaction. However, it does invert the reactivity of the halogen series where iodine becomes the more reactive. Questions on Sn2 so far? Okay. Okay, but we can trick it, okay? And we can do that by playing the game where we're looking at the kinetics versus the thermodynamics, okay? Remember, in thermodynamics, we want the bond that is the strong, that has the stronger bond, the tighter bond, the shorter bond, okay? So in the case of this reaction here, we have an alkyl halide, in particular the iodine. We have a chloride ion as our nucleophile, and we are doing it in acetone, okay? So let's see, if chloride is the nucleophile and we're in acetone, that's a polar aprotic. So that means chlorine is more reactive than iodine, okay? So chlorine is more reactive than iodine because we are on a non-protic solvent, okay? So that means the equilibrium is going to lie to the where we're forming the shorter bond, the chlorine-carbon bond, and the weaker nucleophile in this set. So that makes this the thermodynamic product, okay? And if we think about which is the stronger base, okay, iodine has, the conjugate acid has a pKa of -8, HCl has a pKa of -6. So if we subtract that from 14, iodine is the weaker base in this case because the stronger acid becomes the weaker base. And therefore we have the thermodynamic product. We form the weaker base, we form the stronger bond, we have the right reaction because it's the thermodynamic product. However, we can trick it by converting it to the kinetic product. Okay. So, and the way it's done in this is that we can actually go in the reverse reaction if we have a salt that is soluble in acetone. For example, the iodine here is soluble in acetone. And when it reacts as a nucleophile, even though it's the weaker base, and in this case, it's a polar non-protic solvent, aprotic solvent, it's the weaker nucleophile. If the reaction does progress to here, what happens is our chlorine precipitates out. So while only a little bit of the reaction is actually going in that direction, remember this is reversible here, only a little bit is going in that reverse reaction, but instead of having this lithium chloride, which is soluble in acetone, we have sodium chloride, which is not soluble in acetone. So even though there's only a little bit of this back reaction in the previous system, we've actually been able to form the kinetic product, the one with the weaker base, the one with the weaker nucleophile, because we're removing the other nucleophile from the reaction. Okay, so that's another important thing to remember about solvent is that we can get our reversible reaction to go in one direction or the other, depending on the solubility of our reagents. Okay, so we also talked about the reaction rate of the structures. Yeah, this is it. And that the methyl group with only hydrogens is more reactive because of sterics. The primaries are more reactive because of sterics. Then by just adding a second one here, the sterics are starting to come into play.
And by the time you have 3 of them in here, the rate is practically negligible. You'll get less than 1% every time. Okay. And that has everything to do with that steric hindrance, that increase in activation energy to repel all the electrons from this transition state. It has to repel a whole bunch of electrons just to get in there and start to form the bond. And that gives us that higher activation energy. And therefore it's so high, it's above like it's more likely to break down and decompose. And there's other reactions that can happen at a lower energy. So you're going to have something happen, but it's not going to be an Sn2 reaction. And we'll talk about that actually in the next section. Okay, so even having bulky groups that are one system off right here, we have a primary alkyl halide, but as the groups attach to that primary alkyl halide work, it also does that. So I have already lectured on this. Okay, I'm sorry. I thought we were there. All right, so let's move on to section 3. And oh, darn it. I thought I was on the other section. Okay, so now we're going to talk about those Sn1 reactions. So in Sn1 reactions, the first thing that happens is we form a carbocation. Okay, and the way that we form that carbocation is the idea that we are going to break that bond first. So in that previous energy diagram with the Sn2 reaction, we had a tertiary alkyl halide and it had a high activation energy. Well, the activation energy for actually breaking that bond to form that carbocation is lower than the activation energy required to do that Sn2 reaction. That's why we don't see the Sn2 reaction, because it has a lower energy and we actually end up going through the different mechanism. All right, yeah, admit somebody. Okay, so now that we're going through that different mechanism, and it is this mechanism where we form that carbocation intermediate. So the stability of that carbocation is one of those things that's going to tell us about how easy it is to form and then what it can react with. Okay, so let's think about this carbocation for a minute. This carbocation has changed its hybridization state. Okay, we went from an sp3 hybridized carbon right here. We broke a bond here, and then we turned into an sp2 hybridized carbon with an empty p orbital. Okay, this is important for our product ratio because your nucleophile can attack at the top or attack at the bottom. There's no difference in energy between the top or the bottom. Okay. So, and the other thing it gives us is now that that intermediate, that carbocation, is more reactive, we can actually use weaker nucleophiles to react with it. So notice that water was one of our poor nucleophiles here because all it had was lone pairs. It didn't have a charge. But now that we have a charge on the carbon, it makes it easier for it to react to give us our protonated intermediate here, which then has to lose a proton to become the neutral final product. So that's another advantage of the Sn1 reaction. We can actually make things with poor nucleophiles that we couldn't make with an Sn2 reaction. Okay. Now, with that ability of going through that trigonal planar system, we can actually get reaction at the top or the reaction at the bottom. Okay. Meaning if you started with an optically additive compound, you're going to get a mixture of the R and the S because it'll make the R coming from one direction, it'll make the S coming from the other direction, giving us our mixture of products. And so we can go from something that has optical activity, because we have a pure isomer, stereoisomer, to having a mixture of R and S, and it becomes inactive. And we call that a racemic mixture. But remember, that's different than Sn2. In Sn2, we get inversion of stereocenter, flipping that umbrella back the other way. We get inversion of stereocenter, and so we still have optical activity in an Sn2 reaction. So this is actually one way to probe whether your mechanism is Sn1 or Sn2. You look for the amount of optical activity at the end of the reaction. And you can even see if they're competing, because if you have a pure Sn2 reaction, you're going to have 100% of optical activity. If you're pure Sn1, you're going to have 0 optical activity. And if you have a mixture of 2, you're going to have less than 100% optical activity. So you can actually look for competing mechanisms within the same reaction mixture just by looking at the stereochemistry. Okay. So in this case here, we're actually taking that bromine off using another poor nucleophile, water, and it is going to give us that mixture of R and S for our system. And unless we separate them by some other method, we are going to have an optically inactive mixture. Okay. So that leads us to a bunch of reactions we can do with really, really poor nucleophiles, really, really weak. But notice this all happens in polar protic solvents. The carbocation system is supported by polar protic solvents, and so we like to see that used a lot in our Sn1 type reactions. So another thing when you're looking for, well, what mechanism is this using for? Look at the solvent in the system and figure out what the product is, and you'll see what's happening. So if we have water, it's hydrolysis, we can make ethers, or we can even make esters from the system using a carboxylic acid. Okay. So in almost all cases, well, no, that's not true. In a lot of cases, we'll use polar protic solvents because the polar protic solvents will hydrogen bond to the leaving group. They will tightly hydrogen bond to the leaving group, making it easier to leave. As soon as it's hydrogen bonded to the leaving group, then the negative side of the water, in this case, the oxygen here, can help support the positive charge on that carbocation. So we're using hydrogen bonding not to activate or deactivate a halogen, we're actually using it to support a halogen to make it easier to leave. Okay. So, and I think we did, yeah, here we go. We did that. So just by changing that ability to hydrogen bond, we can actually change the rate of that reaction. In this case, there's less water to hydrogen bond. That less water to hydrogen bond makes it less reactive because it's harder to remove the halogen. Because remember, that's the first step. We got to form that carbocation first. Okay. So for Sn1 mechanisms, polar protic solvents must be used. You have to have at least something in there that is polar and protic to hydrogen bond to your leaving group. It's different from the Sn2 reaction where polar aprotic solvents increase the rate. Okay, Sn2s will occur in polar protic solvents, but react faster in polar aprotic solvents. And don't forget, in Sn2, we also have a change in reactivity in the halogen series. In an Sn1 reaction, is very unlikely to occur in an aprotic solvent. In fact, if we looked at something like just the relative rate here, we just used a polar solvent that's aprotic. This is the dielectric constant, gives you an idea about it's how polar it is. And say its relative rate of 1. Okay, just by switching to something that it still has a little bit of van der Waals forces because of the 2-carbon chain, but it has a hydrogen bonding species, we've increased the rate by 200 times, okay? Making that even smaller and more polar. Notice this is about the same polarity right here, but it's 200 times faster. If we increase the polarity in methanol, it goes to 1,000 times faster. And then if we, here, let me check my internet connection. It says it's, yeah. Hang on, I'm switching internets right here. There we go. That should be more stable. If we go to water, which is the most polar of this, and it can hydrogen bond on both sides, it increases the relative rate to 8,000 times. Okay. So what if we went the other way? Let's go to something that's non-polar and aprotic and has a very poor system. Well, the relative rate is less than 1/10 of 1%. It almost is negligible, the effect of the reaction in hexane. And diethyl ether, which is also fairly not a little bit polar, but it's aprotic, has a very poor reaction rate. So in our Sn1 reactions, think, oh, what solvent am I in? Okay, I'm in a polar protic solvent. Okay, now I have to compare Sn1 and Sn2 and what my nucleophile is. Okay, so let's compare and contrast Sn1 and Sn2. Okay, the first thing is look at the reaction coordinate diagram. In Sn1, you're only ever going to have one hump because you have one transition state. The nucleophile and the electrophile are in the same place at the same time. A bond is forming and a bond is breaking. It's concerted. It happens in one step. Okay. Now, if we look at the coordinate reaction diagram for an Sn2, we have to form the carbocation, and that's the first step. Okay. That's the slow step because it's got the highest activation energy. Okay. So we have this activation energy that gives us our intermediate, and then that intermediate reacts. And in this case, it's reacting with a negatively charged ion, so we don't have that third step. If it reacts with a neutral molecule like water or methanol, we have to remove a proton, and there's a third step in the system. But in an Sn2, you'll have at least two humps because you have to form the carbocation intermediate. Okay. In the Sn1, the Sn2 reactions, we're looking at these as exothermic and exergonic. They are spontaneous once you have enough energy to overcome that energy barrier. And in the Sn1 reaction, we're actually endergonic and endothermic to form the intermediate. Okay, the intermediate is higher in energy than the starting materials. So that first step is endergonic. That first step absorbs heat. Now, once that intermediate reacts, the net reaction is exothermic. Okay. So in an Sn2 reaction here, the nucleophile is typically negatively charged or has a partial negative charge. Okay. We have to have a good nucleophile. So it's typically something with a negative charge on it, or something that is a shared negative charge, like a carboxylic acid, where it has a partial negative charge. Okay. That's not true for the Sn1 reaction because we formed the ion on the substrate, and therefore even weak nucleophiles will react with it as a neutral species, just sharing those lone pairs. When it starts to share that lone pair, then it can proceed to product. Okay. In the case of our Sn2, the nucleophile donates the electrons and the leaving group takes the other electrons away. In the Sn1 reaction here, the nucleophile actually is using a lone pair to create that new bond. Okay. Aprotic solvents destabilize the nucleophile because it can't fully support it and therefore decreases the rate of the reaction. And it increases the rate of the reaction because of the higher energy barrier. So the polar aprotic solvents have a higher activation energy than our polar protic solvents. Okay. In the case of Sn1, we almost always use polar protic solvents to decrease that activation energy. In a polar protic solvent, it makes it very easy to get that first activation energy. In a less polar solvent or a non-protic solvent, that energy barrier goes up. Okay. So we can tell a lot from our coordinate diagram on what's happening in the reaction. Questions on comparing Sn1 to Sn2? Okay. So what other things affect Sn1? Well, let's see, we have to form a carbocation. So that means a tertiary alkyl halide, tertiary, is going to be faster because it's easier to form that. So it has a lower activation energy. So tertiaries are going to be faster than secondaries. And then primaries and methyls are going to be kind of hard to do because those are not very stable carbocations. Okay. But what else do we have here going for us? Well, in this case here, we have increasing stability due to our hyperconjugation of our groups being able to donate into that carbocation. But the other thing we can do is use resonance stability to increase the stability of a carbocation. In this case here, this is still, not a full positive charge, but the entire positive charge is centered on that single carbon. if we have a resonance structure here, we can share that positive charge over 2 carbons. So each carbon only has 50% of a charge, meaning it's more stable than the tertiary carbocation. And in the case of if we formed a positive charge over here on this benzylic position, this methyl group outside of the benzene ring, it can actually stabilize the charge on a total of 4 different atoms. Okay. Now, these are not equally shared with this one right here because they would have to break aromaticity to do that, but it's still sharing some of that charge with the benzylic. And so it's more stable than the tertiary as well. So what does that look like? Okay. All right. So why? Okay. So in the case of the allylic system here, we have that empty p orbital, right? And if this empty p orbital lines up with the 2 p orbitals of our double bond, they can share that charge and resonance stabilize across the whole system. Remember, in our tertiary carbocation, we have to rely on an inductive effect from the carbons and hyperconjugation. And remember, hyperconjugation is the sigma bond between the hydrogen and the carbon can line up with that empty p orbital to help stabilize it. It kind of donates a little electron density through space. And if you only have one, you only have a little bit of donation. But if you have 3, you have 3 different ones that can donate here, all 3 sides, and that helps stabilize the reaction. How would you use an Sn1 reaction and an Sn2 reaction in the real world? That's a great question. Okay. And the truth is, okay, let's see. Sn1 reaction we use for making alcohols from alkyl halides. So let's say you wanted to make a tertiary alcohol. Okay. You couldn't just take a tertiary alkyl halide and hit it with hydroxide ion because it doesn't like to do that Sn2 reaction. So what we do is we take that tertiary alkyl halide, reflux it in water, make it form the carbocation, and then the water reacts to give us our tertiary alcohol. But let's say you want to make a primary alcohol. Okay, you couldn't boil a primary alkyl halide in water and make it go through a carbocation. And water is not a strong enough nucleophile to make the alcohol. So in that case, you would actually want to boil your primary alkyl halide with a hydroxide ion, which is a good nucleophile, to displace your halogen. So that's how you can get a primary using an Sn2 reaction, but a tertiary using an Sn1 reaction. Does that answer your question? All right. Actually, great question. Okay. So because of that resonance stability and the fact that it has an ability to spread more charge out over it, they are actually more reactive than that tertiary carbocation. Okay. So the resonance is giving us high reactivity for the benzylic and the allylic system, with our secondary and our tertiary being the next most reactive. And these almost never do Sn1 reactions. It's very hard to form the primary and the methyl carbocation in a solution. So you can only do it in gas phase. So if you have a primary alkyl halide, it's not going to do Sn1. If you have a methyl halide, it's not going to do Sn1. Okay. But any of these, in fact, with the benzylic and allylic, it's more likely to do an Sn1 reaction because of that stability. Okay, so the other thing we also want to remember is we're only going to do the substitution reactions, either the Sn1 or the Sn2, on sp3 hybridized carbons. We are not going to displace by us. Whoa, okay, where it is. There. We're not going to do a substitution reaction by displacement here because we have no way to get 180 degrees apart from your leaving group here because of sterics. And we're not going to do an Sn1 reaction because that's a very unstable cation. Okay, so, and if we want to look at it from the perspective of where the lone pairs are, the lone pairs are, the p orbitals are here and here, and so we can't actually have a nucleophile come in and react. It's more likely to come in and act. The pi bond is more likely to act as the nucleophile because it's electron rich. And we're not going to break this bond to create this system because that lobe, this cation, is in an sp2 hybridized orbital, and the pi bond is still intact. Remember, when we formed the regular carbocation, it was an empty p orbital. Okay, this is an empty sp2 orbital, and it's not very stable, and it does not form. Okay, so there's a couple things that enhance the rate of the reaction, and one of the things we think about is it more like is the intermediate more like the product or more like the starting material? So in the case of our Sn1 reaction, it's more like our product because we've changed the system. And so it actually takes a significant amount of energy to break that bond first. Our intermediate, the carbocation, is much higher in energy than our starting material. And so we're looking at it as our intermediate then is much closer to our product, and therefore it takes energy. Product, and it takes energy. Okay. So if it takes energy to form that carbocation, and everything's trying to minimize the amount of energy it takes, we have an issue now if we have a secondary carbocation. If we have a secondary carbocation, it's not as stable as a tertiary carbocation. So the clever little molecules are going to say, hey, do I have something on an adjacent carbon? Do I have an adjacent carbon that can form a tertiary carbocation? And if the answer is yes, how is it going to do that? Well, it's going to do that by either moving a carbon bond, which we call a methyl shift or a methyl migration, or a hydrogen is going to move over one atom to give us the higher stability tertiary carbocation. Okay. It rarely happens going from a secondary to a secondary. It usually is a secondary to a tertiary. You're trying to form the most stable system here. Now, how does that work? Well, we have 2 electrons in our sp3 hybridized sigma bond here, right? And what's going to happen is it's going to start to see, oh, I have a picture down here actually. It's going to start to see this empty p orbital right here. And it's going to start a little bit of hyperconjugation going to it. And it's going to say, hey, if I start sharing my electrons with this empty p orbital, I'm going to end up with a tertiary carbocation. So it transfers both of his electrons over one carbon, and it ends up with having a new tertiary p orbital with 3 different hyperconjugation interactions with that empty p orbital. So the driving force is the idea that we're going to make a more stable system, and it does it by moving both of the electrons from the sigma bond over to the new, giving us our new empty p orbital on our more stable carbon. It doesn't have to be a methyl group. We can do it with hydrogen too. Now notice we call it the hydride shift because we're moving both electrons with the hydrogen. So we're not talking hydronium, we're not talking proton. We're actually talking hydrogen with both electrons moving over. And hydrogen with both electrons is called a hydride because it'll have a negative charge, and it moves over one. Now this is also called a 1-2 shift, okay, or a methyl or hydride migration. And so we're basically looking for 1-2, so it's just going over one carbon. It'll only ever move one carbon, and it'll only move to the more stable carbocation. Okay. Okay. So let's look at what that reaction diagram would look like. Okay. So if we have a carbocation rearrangement, there has to be an energy driver for it. So the first thing we have is we go through our transition state and make our first intermediate. Our first intermediate is our secondary carbocation right here. But that secondary carbocation, notice, is higher in energy than our starting material. So it's endergonic or endothermic. Then there's a barrier to that hydride or that methyl shift. Okay. But once it overcomes that barrier, we actually are exothermic to our next intermediate. Okay. So even if this intermediate was higher in energy than our starting material, we still gave off heat.
to make that tertiary carbocation. Okay, and then the net reaction is going to be our last transition state going to products here. So this change in energy from the second to the tertiary is the driving force for making this shift from the secondary carbocation to the tertiary carbocation. Okay, so one example is the idea that we can have this go from a, okay, so, well, it's not very common for it to go from a secondary to a secondary. It can happen. And we know this because of product ratios in a reaction. So for example, we're going to do a reaction where we have this OH group, okay? And we're going to displace that OH group with a bromine by making the OH group a good leaving group. Remember, OH by itself is a very strong base. It's a very bad leaving group, okay? We want a weak base to be a leaving group. So what we're going to do is we're going to protonate that alcohol to give us the alkoxy, the protonated alcohol, and then that turns it into water. Water is a good leaving group. And then we form our secondary carbocation. And then our secondary carbocation can immediately react to form our 2-bromo pentane here. Okay. But what if we had a hydride shift? Okay, it can't move this direction because that would give us a primary alcohol, primary carbocation. So the only direction it can move to this way to give us another secondary. Okay. Now, it gives us a secondary that's in the middle. And so it actually has a little bit more of the inductive effect because it has more carbons on either side. Excuse me. So it's slightly more stable. But we know it happened because we have a little bit of this 3-bromo pentane in our reaction product. So it doesn't happen all that much. It mostly happens between a secondary and a tertiary. So when you're doing your homework and you form your carbocation and it's a secondary carbocation, look to see if you can move that carbocation 1 carbon over and make a tertiary. If you do, it's going to be one of your reaction products. The other weird thing that can happen is, it doesn't have to be just a methyl group. If you have a ring and that ring has any ring strain at all, you are going to expand that ring to make that tertiary carbocation. So in this example here, we have cyclobutane. And remember, cyclohexane is the only ring without ring strain. So that means the cyclopentane and the cyclobutane have a significant amount of ring strain. And so being able to open that ring up and relieve some of that strain is going to be favorable. And again, we're going to do the same thing. We're going to turn the alcohol into a bromide, but OH is a bad leaving group, so we protonate it. And then what can happen is now we have a secondary carbocation here, but we have ring strain. And so we're able to break this bond, move over 1, taking both electrons with us. When we do that, we now have a tertiary carbocation. Because notice that we had a methyl group here, we have this bond here, and we have this bond here. Those become the 3 things bound to here. And another driving force besides being a tertiary carbocation is we've actually relieved a lot of ring strain. Okay, so look for whenever you have rings near carbocations, look for it to expand up to 6. So 4s and 5s will expand up to 6. You won't expand from 6 to 7 typically, but because that is more ring strain. So and then our final product is the bromination of our tertiary carbocation. All right, questions on carbocation rearrangement. Remember, when we started this chapter, it was like several things can happen in the thing. We can add a proton, take a proton away, break a bond, react a nucleophile with an electrophile, or rearrange. Okay, so this is one of those 5 or 6 things that happens in mechanisms every time. Okay, so let's look at this from the perspective of the Hammett principle here. Sn2s always give an exothermic product because we have a single transition state. We're forming a bond and breaking a bond. And that intermediate looks much more like the starting materials because the nucleophile has to start forming the bond before we start breaking the bond in the leaving group. And it gives us that
exothermic reaction. However, the first step in an SN2, in an SN1 reaction, the product looks much more, the intermediate looks much more like a product, because the product of this step is our carbocation right here. So this is starting to look more like our product because we're breaking this bond more than having that nucleophile come in. We're breaking the bond first. Therefore, we're making this quote product, this intermediate, that is endothermic. So if we want to think about it in that situation, then of course it has to react and come back down to products. Okay. So let's see how to tell if an SN1 or an SN2 reaction is happening. Okay. So let's look at it from the perspective of what the intermediates might be. Okay. So let's say we have this methyl bromide. Okay. And to make that bond break, because that carbon is not a very stable carbocation, we're going to have a very high activation energy to get it to break that bond first and give us our carbocation. Okay. Which means that it's probably not going to go SN1 because it has an unstable carbocation. So it's more likely to give us an SN2 reaction. In contrast, the breaking of that bond to form a tertiary carbocation is a much lower energy barrier. And we know that this intermediate is, overall relatively much more stable than that primary. And therefore, we're probably going to have that SN1 reaction because this is easy to form and has low activation energy. But we're probably not going to do an SN2 because of sterics. The sterics of this system here makes an SN2 less likely to happen. All right, so what's the other way to think about it? Okay, well, instead of just looking at the electronics and that energy barrier, let's look at it from the point of an SN2 reaction. How likely is the SN2 reaction going to happen? Well, in the case of this, if we have a good nucleophile, usually it's something with a charge or a nitrogen that it's going to come in, and we don't have a high steric demand, our activation energy is going to be low. And so if we don't have a steric demand and we have a good charged nucleophile, we can encourage an SN2 reaction to happen. However, if we have something that has 3 different groups on it, that nucleophile can be as good as it can be, but our activation energy is high. Our activation energy is so high that it's above the activation energy of the SN1 mechanism, and therefore it's less likely to happen. So in almost all cases, tertiary alkyl halides do not undergo SN2 reactions. Okay, let's see. So to kind of bring it down into pulling the whole thing together, tertiary alkyl halides only go by SN1 mechanism. Okay, just too much sterics and you can't do it. Methyl and primary alkyl halides only go SN2 reactions because they can't form a stable carbocation. The secondary alkyl halides are always a little bit in competition between the SN1 and SN2, but by looking at the solvent, the leaving group, and the nucleophile, you can see which one is going to give you the major product. A very good leaving group, a poor nucleophile, and a polar protic solvent will give you an SN1. It's a good leaving group because it wants to leave. It's a polar protic solvent because it's going to hydrogen bond to that leaving group even before it comes off. And we think of poor nucleophiles, uncharged things, because you have to form that carbocation first. Okay. Now, you can encourage it to go SN2 by having a decent leaving group, like chlorine, a high concentration of your nucleophile in a polar aprotic solvent. Because you're in an aprotic solvent, you're kind of eliminating some of the SN1 product and you're allowing it to be an SN2 mechanism because you can't stabilize that carbocation, you can't stabilize that leaving group as it comes off. So when we're trying to compare and contrast, tertiaries, SN1. Methyls and primaries, SN2. Secondaries, look at the leaving group, the nucleophile, and the solvent. Okay.
So I think we can also look at this from a table perspective, is the fact that we can form carbocations in the primary and the secondary. They're fairly stable, which means they're available for SN1. Okay. Now, these cannot form stable, so they don't do SN1. Okay. Now, all of these, if there's not too much sterics in the way, and we use the right solvent, we can do SN2, but tertiary never does SN2. So the only one we really have to worry about is the secondary, okay? And when we look at the secondary, we have to look at good leaving group or okay leaving group, good nucleophile or poor nucleophile, protic solvent or non-protic solvent. All right. So let's attack it. How would you solve one of these in your homework? Well, first thing we want to do is we want to add all our lone pairs, because we want to see where there's a full charge and a partial charge, and if those lone pairs can act as a nucleophile or not. The second thing we want to do is identify what is the nucleophile and what is the electrophile. When we're talking about alkyl halides, we have that polar bond between the carbon and the halogen, and therefore the carbon center is our electrophile. The nucleophile is typically the thing with lone pairs or a negative charge. Okay. Now we look at the electrophile and see, is it easy to form a carbocation, or does it have a steric demand on it? Okay. So things like allylic, benzylic, and tertiaries are going to easily form carbocations that are stable, and therefore you're going to be looking at those as probably maybe an SN1 reaction. The primaries and the methyls are only going to do your SN2s. The secondary, you have to start looking at solvent. So that's our next step, is it a polar protic solvent or polar aprotic solvent? Polar protic solvents support SN1 reactions. At that point, you should have enough information to definitively decide between SN1 and SN2. And if not, go ahead and start pushing electrons around with arrows to prove to yourself that it's an SN1 or an SN2 reaction. Any questions on this? This strategy will help you with all of your homework, by the way. Well, not all, but some of it. Okay, so in summary, we want to look at the types of nucleophiles we have. Okay, so weak bases that have a negative charge on them are good nucleophiles. Okay, notice all of these where the conjugate acids are really strong. If we went and did the conjugate acids of these, they would be fairly strong. And so they're weak bases. They have a negative charge, and they're polarizable. Sulfur's big, bromine's big, iodine's big, and this has resonance. So that's why they're good nucleophiles. Okay. Our weak bases, but fair nucleophiles, are those that have either a shared charge. For example, this can be shared over 2. This can be around the ring by resonance. This is a smaller ion. It's not as polarizable. That's why it's a fair nucleophile. Okay. And notice this one isn't charged at all, but it's got a big fluffy sulfur. The next thing we want to look at is is it a strong base? Hydroxide and alkoxides are strong bases, right? And if they're small, like methanol, ethanol, or methoxide, ethoxide, and hydroxide, they're also unhindered bases. They are small and act as good nucleophiles. Okay, they're still strong bases, but they're good nucleophiles. Now let's go to strong bases, but because of sterics, we have a whole bunch of stuff around here. Because of sterics, it cannot act as a nucleophile. It's still a very strong base, but it can't act as a nucleophile. Okay. So then we go to weak bases and poor nucleophiles. Whenever we see a weak base or a poor nucleophile, so hydrogen sulfate right here, a phosphoric acid, or actually that's not phosphoric, that's phosphate. alcohols, neutrally charged species, or things that are monoprotonated, are poor nucleophiles and weak bases. Okay, so Sn2, one hump, one transition state products. Sn1, at least one intermediate, at least a carbocation. And so you always have at least two humps, sometimes three. All right, questions on comparing Sn1 to Sn2? Okay, let's see where we are. Okay, good. We have enough time to move on to chapter 7. Okay, so in this module 6, okay, we learned about different types of reactions. We learned about energy diagrams, and we learned about mechanism, how to push electrons around to get us to where we're going to be. And up to now, we've been doing substitution reactions where we're starting with an sp3 hybridized carbon, and we're going to an sp3 hybridized carbon with a different functional group. Okay, and so choosing the nucleophile will change whatever functional group we have to make them interconvert between different things. Now we're going to look at those same types of mechanistic steps, but instead of substituting something, we're actually going to change the hybridization from an sp3 hybridized carbon to an sp2 hybridized carbon, which is going to form an alkene. And when we lose a thing off one carbon and a thing off an adjacent carbon, we call those elimination reactions. And the first elimination reaction I want to talk to you about is E1. Okay, so just like in the Sn1, you form a carbocation. E1 is unimolecular, and we're going to start with forming a carbocation first. Okay, so like I said, instead of displacing it here, we're going to have a leaving group on one carbon. Notice we're calling that our alpha carbon right here. And then there needs to be a hydrogen on one carbon over in some direction for it to leave. So we're going to pull this hydrogen off and use these electrons to kick in here and give us our double bond. So we're eliminating our leaving group and one hydrogen. Okay, so that's the important part here. The leaving group leaves, but you also remove a hydrogen. So I think there might be a base involved in removing that hydrogen. Okay, so to make sure that we have some nomenclature that lets us talk about which carbon's going to lose the hydrogens, let's talk about how we're going to label them right now. So we're going to start with whatever functional group we have here, and then we're going to say, okay, that carbon right from that functional group is going to be our alpha carbon. That's the one that's attached to the functional group. It's in the case of this one right here, it's the one with the leaving group on it. Okay, so the alpha carbon is going to be the one with the leaving group on it. All the carbons that are bonded directly to that alpha carbon are called beta carbons. Okay, so we're going to remove something, the leaving group from the alpha carbon, and a hydrogen from one of the beta carbons. But we have to make sure we pick the right one. Okay, and then we actually also have the next thing over, it would be the gamma hydrogen, the gamma carbon, and those would have gamma hydrogens on it. Okay, so it's the hydrogens bound to the type of carbon. So it's the alpha hydrogens and the beta hydrogens are on the beta carbon. So our leaving group is in the alpha carbon, our hydrogen is on the beta carbon, and we need to choose the right beta carbon. Okay, so we'll get to that. Now, why? Well, because alkenes have different stabilities. We talked about this in our nomenclature chapter, and the idea that different types of alkenes have different stabilities. Okay, so an alkene with a single substitution on it is not as stable as one with two substitutions on it. Okay, so in this case here we have a one attachment, here we have two, and this happens to be the cis configuration because they're both on the same side, and the cis configuration is not as stable as the two in the trans configuration because of sterics. Okay, so when we go to that, we can also get another one is the two on a single carbon, which actually is, this carbon is more stabilized than that carbon, but it's still slightly more stable by 3 kcals per mole.
And then notice once we get to 3 substitutions, it's even more stable, and 4 substitutions, it's very stable. Okay, so if the terminal or the one substituted is the least stable, and the more substitutions we get, the more stable, that means that we might want to use this scale of stability to help determine what our product will be from our reaction. Okay, so the whole reason it helps is because of hyperconjugation. Remember that, excuse me, the double bond is two p orbitals right here. And we have the sp3 hybridized orbital bonding to the hydrogen, sp3 that can bond through space through hyperconjugation to help stabilize it. So the more of those you have, the more stable it will be. Okay. So these are all within about 5 kcals per mole of each other. This has sterics, this has no sterics, and this is double hyperconjugated on a single carbon. But now we get 3 hyperconjugations and 4 hyperconjugations. So that hyperconjugation is what's helping stabilize those double bonds, making them more stable than the less substituted. It's kind of like carbocation stability. The more things you can hydrogen bond to, the more stable that carbocation is. Okay, so let's talk about our elimination reaction. And in the case of an E1 reaction, we're going to do the exact same first step as we did with an Sn1 reaction. Okay. In fact, many times an Sn1 reaction is competing with an E1 reaction. And the thing that's going to change it is how strong our base is. Okay. So let's look at that one step at a time. Okay. So in the case of, there we go. In the case of our system, what we're going to do is we're going to use a polar protic solvent to make our carbocation. And that's the first thing that's going to happen. We're going to make our carbocation here. Okay. Now, 2 things can happen. Okay. The lone pair of the oxygen can act as a nucleophile and react with the carbocation center to give us our protonated species, which then can lose the proton and give us our substitution product. Okay, so we have our polar protic solvent, which is methanol. It's not a very strong base because it's neutral, but it does support a carbocation. Okay. Now, the other thing that can happen is once we form this carbocation, our methanol, which was acting like a base here, can also act like a base here, pull off a hydrogen on that beta carbon, leaving the electrons behind to form our double bond, giving us our alkene or our E1 product, our elimination product. Okay. So just like an Sn1 reaction, the E1 reaction also only is dependent upon the concentration of the substrate. Okay, so it's a first order reaction. Now, notice that we have a weak base in the system, and the weak base favors the Sn1 reaction. The stronger the base, the more it will favor the elimination reaction. Okay. All right, any questions? No. What do we have to? 3, 7, okay. So let's think about if we were just looking at the E1 product, okay? So we form that carbocation, and then we have to have something act like a base. Now, in this case, this is your classical Lewis base because it's got a lone pair. That lone pair can reach out, grab that hydrogen, leaving those electrons behind. Those electrons are going to then rehybridize and turn into a p orbital. You already had an empty p orbital on the carbocation, and so both of those orbitals will be occupied by those 2 electrons, and we form our alkene or our E1 product. Okay. So what would the reaction diagram look like? Well, the reaction diagram has to have 2 humps because we have to form that carbocation intermediate. So if we look at that, and
we look at the two different activation energies, because in that example here, we had a competition between the Sn1 and Sn2. Let's look at why they're in competition here. So the first step is the same for either mechanism. We have to form that carbocation intermediate, okay? So it looks identical up to now. The only difference is the activation energy for the substitution is lower than the activation from the elimination. The reason the activation for the substitution is a lower energy barrier is that the methanol is not a strong base. If it was a strong base, this would be the smaller activation energy, and it would be down below here and favor the elimination product. But it's not, and therefore we end up with the less stable material being at the 20% and the substitution product being at 80%. Okay, or about. Okay, so in this case here, we almost always have a little bit of competition between an E1 and an Sn1. However, looking at the strength of the base or the size of the base, we can choose whether it's going to go the elimination route or the, so let me talk, well, I have a slide on that. Okay. So in an E1 reaction, we actually can change one product or the other by changing the temperature, okay? Higher temperatures result in more collisions and more energy, and therefore you can go through either barrier because you have enough materials. The Sn1 reaction will always produce a little bit of elimination products, okay? But if you heat the reaction, you can favor the okay? So the temperature will change the ratio a bit. However, with a poor nucleophile, the Sn1 will dominate. With a poor base, the Sn1 will dominate. And generally, it's a little bit hard to choose one or the other, but higher temperatures do start to favor the E1 product. Okay. So at low temperatures, we have a weak base as a nucleophile and our tertiary carbocation, and that makes it Sn1 favorite, okay? We have the elimination barrier is higher than the Sn1 barrier, and therefore we have very few molecules that have enough energy to go that second energy barrier. So the first lower energy barrier is favored, okay? So at lower temperatures, the Sn1 is favored. If we raise the temperature or use a stronger base, we can favor the E1 reaction, okay? So technically, we rarely use that Sn1 reaction synthetically because there's always going to be some elimination products, and you're always going to have a mixture for the system. In that example I said before, where we're making the tertiary alcohol, you're actually going to end up with a little bit of the dimethyl methyl propene as the elimination product from the system, but luckily they're easy to separate, and so you can actually use that. So we really want to look at this this approach with instead of using the Sn1 reaction, increasing the base strength and making it into an E1 reaction. Okay. And then there has to be an E2 reaction, and I'll talk about that in the next chapter. Okay, so we talked about the fact that we want to form the more substituted because it's more stable. Well, we have a rule for this. We call that Zatev's rule. Zatev's rule tells us that we want to look at the different types of beta hydrogens we have, and the beta hydrogen that will give us the more substituted product is favored, okay? The beta hydrogen that gives us the more substituted product is favored, okay? So let's look at our competition between our E1 and our E2 here. So we have our substrate right here, and so we have a bromine on here, but we have a methyl group here, we have a methyl group here, we have an ethyl group here, okay? So we have two kinds of beta carbons. We have
a primary beta carbon right here because it has 3 hydrogens on it. We have a secondary beta carbon because it has 1 carbon bonded to it. Okay, so we have 2 kinds of beta carbons. Okay. Our first step in our E1 or Sn1 reaction is to create our carbocation. So that's what we're going to do. We're going to create our carbocation first. Okay, so because methanol is a weak base, we're always in competition with the substitution product. And what will happen for that is we'll just get to this ether right here, but that's just our substitution. However, if we remove the proton from this primary alpha beta carbon, we're going to end up with a di-substituted alkene, which looks like this. Okay, it's like, oh, di-substitute, that's not too bad. Okay, however, if we went over here and instead remove the beta carbon from the secondary carbon, we will end up with the double bond forming between those two, and we're going to end up with the tri-substituted. Okay, so Zaitsev rule tells us if we're going to end up with the most substituted alkene because it's more stable. Okay, so what we're going to have that is you start looking for the beta hydrogen that will give you the more substituted alkene. Okay, so of the alkenes, the major product will always be the more substituted. And if we changed our base up here from methanol to something stronger, we can actually make it more of the elimination product happen. Okay. So let's look at that from a coordinate diagram perspective here. So the idea here is that the intermediate to form the pull the proton off of the more substituted one here is actually a lower activation energy than to try to pull it off of the less substituted carbon. Okay, think about it. This carbon here is more able to spread those electrons out than this is because it has 2 carbons here bonded to it, not just the 1 carbon bonded to the carbocation, and therefore it's slightly lower in activation energy than eliminating the one from the only primary carbon here. Therefore, even though our activation energies are similar, our elimination product from our more substituted beta carbon is less, and therefore it becomes the major elimination product. Okay. So how can we use these? Let's get into a real world reaction and how we can do this. What we're going to do is we're actually going to use a weak base that's a poor nucleophile. So in this case here, we're going to eliminate an OH group using acid. Okay. So the first step is going to be, of course, protonating here. And when we do that, we have a choice of this beta carbon, which is a primary, this beta carbon, which is a primary, and this beta carbon, which is a secondary. So just identifying that, we should know that our double bond is going to be formed between the alpha carbon and the secondary beta carbon. So that gives us our major product as the tri-substituted and our minor product as our di-substituted. Okay. Just using Zaitsev's rule and using the idea we want something more substituted. Okay, let's move it around so we only have a choice between a primary and a secondary here. And let's look at our product ratio there. Again, we get a little bit of that primary beta elimination, giving us our terminal alkene, but our terminal alkene is the least stable of the set, right? We also can eliminate it where this methyl group has rotated around here and it gives us the cis isomer. But remember, the cis isomer is less stable than the trans isomer. So it's of a little bit of that. And our trans isomer is the major product. The trans isomer is major product because it's the most stable of the 3. So that means it must have the lowest energy barrier to go through that second step of the coordinate diagram. Okay, so yeah, good. Okay, so here's the mechanism. OH is a bad leaving group, so we're going to use an acid to protonate it to make it into the oxonium ion That makes water a good leaving group at this point. It can leave as a neutral species. Okay, so that's going to happen first. Okay, now remember we said this anion right here was a poor base. Okay, a weak nucleophile and poor base. So what's going to happen is we're going to make our carbocation, and then our poor base has time to figure out which hydrogen is more reactive, more acidic. Okay, so if we start pulling on this one right here, we would kick in and give us our di-substituted alkene. And if we pulled it off from here, we're going to give us a tri-substituted alkene. So if we pull it off from that beta carbon that is a secondary, and both of these are primary, we're going to end up with the more substituted product. If we pull the beta hydrogen off the primary, we're going to get the less substituted product right here. And notice where does this proton go? Well, this proton goes back into water, then it can, regenerate our acid here. Okay, so do we understand what our E1 elimination is? Do we understand that we're always going to try to form the more substituted double bond? And we can control the reaction by making sure we're using a base. It can be a weak base. We're using a polar protic solvent so that we can form that carbocation. And that E1 and Sn1 are always in a little bit of competition with each other. Okay. Whoa. Didn't go too far. All right. So let's look at the coordinate diagram for a slightly different compound here. And this compound here has two methyl groups here, and it's got the one here. So what's the first thing that's going to happen? Well, we got to protonate our alcohol. Once we protonate our alcohol, the first thing that happens is we form a carbocation. But what kind of carbocation do we form? We formed a secondary carbocation. Okay. Now we have a secondary carbocation next to a carbon that if it transferred one of those methyl groups over, it would be a tertiary carbocation. Okay, so one of the possible pathways is to create a 1,2 methyl shift to give us a tertiary carbocation. But it's in competition with just transferring a proton. If it just transferred a proton, we'd end up with a terminal alkene that's only monosubstituted. Okay, but the energy barrier to get to that tertiary carbocation is less than just removing that hydrogen. And so we get to our second intermediate, which is our tertiary carbocation. And then, of course, it can act as a base. And depending on which proton it comes off, so it can remove this proton, which is the tertiary proton, or it can remove one of these out here, which is a primary proton. Okay, so that primary proton would give us our alkene out here that's di-substituted. But if it removes this one right here, it gives us a tetrasubstituted product. Okay, so looking at the reason for this is, number one, we are going to try to make our most stable carbocation, but it's going to be in slight competition with removing the proton as a fast step. Once you get to that transition state, you have that carbocation in its most stable form. Now you need to choose which hydrogen is going to give you the more substituted alkene, and that's going to give you your major product. Sometimes it'll ask you for major and minor product, or it'll ask you for the major product. The major product is going to be more substituted alkene. Okay, I'm going to stop here because, oh no, now this is my last slide. So I got 1 minute. All right, so because it's an E1 reaction, we go through a carbocation, okay? And we go through that carbocation, it tells us that we have, we've gone through trigonal planar here, and then we're going to try to figure out which way it's going to give us the most stable product, okay? So of course, our first step in this condition is we're going to protonate, then that's going to give us our carbocation. And our carbocation in this case here is going to give us a product that can be either taking an alpha proton or taking a proton off this carbon, carbon here. But if it's in the elongated form, this strung out form, we're going to end up with our trans isomer. If we have rotated this methyl group around to this side, we're going to end up getting the cis isomer. Okay, so, but remember, the cis isomer is less stable than the trans isomer, and therefore the trans isomer will be the major product. Okay, they can only ever be a disubstituted in this case because we don't have any other branches, so we have to choose between the cis and the trans. All right, that's all I have for today. I'm going to go ahead and stop recording. If you have questions, please stay.